Welcome back. Problem 8-32. So this problem is taken from Mechanics of Material by R.C. Hibbeler, and this is chapter number 8, combined loading. The statement of problem is the horizontal force of P 80 kilonewton acts at the end of the plate. The plate has a thickness of 10 millimeter and P acts along the central line of this thickness such that D is 50 millimeter. Plot the distribution of normal stress acting along section AA. So you can see this is the plate that is fixed support at this end, and there is a P load that applied at a distance of 50 millimeter from this base. Clear? And the length where it is section is 300 millimeter. So you have to find the stress distribution. So let's start with the solution. So first step is that if you cut the beam and draw the free body diagram, so it will be like this one. This is the force P which is acting. This force P is 80 kilonewton, and that is acting at a distance of 50 millimeter. So this distance is in meter, it is 0.050 millimeter. The total length of the height of this beam is equal to 200 millimeter, which is 0.2 meter. So when you cut the beam or section AA, so what you will have a center axial load which is represented as N, and you will be having a moment M. Clear? So what we will do is that we will find this M and normal force N. Let this point is point C. So by using equation of equilibrium, that sum of all forces along horizontal direction must be equal to 0, and force in this direction is taken as positive. So two forces minus 80 kilonewton plus N will be equal to 0. So minus 80 plus N is equal to 0. So it means that N is equal to 80 kilonewton. Okay, so we have this, and now we will find moment, and this we will use sum of all moment about point C must be equal to 0, and taking the counterclockwise moment as positive. So about this point C, one moment is this reaction moment which is counterclockwise, so it will be positive. So M, the another moment that is due to this force into perpendicular distance will be here now as this distance. So you can see this is totally 0.2, so half will be 0.1 meter. So this distance will be equal to 0.1 minus this distance. This distance will be equal to 0.1 meter minus 0.050, which is equal to 0.050. Okay. So let me write it. Distance from this till this is 0.1 meter. 0.1 meter. And the distance is 50 millimeter. Okay. So this distance will be also equal to 0.050 meter. So P into P is this one, and perpendicular distance is this one. Clear? Because C will lies at that point, and it is producing clockwise movement, so it will be negative. So I will write minus P into 0.050 is equal to 0. Okay, so from here you will get movement is equal to 0.050 multiplied by P, and we know that P is given as 80 kilonewton. So 80. So movement will be equal to 4 kilonewton into meter. Now you have this moment. So you can see that due to this is the case of combined loading where you have an axial load, clear, and you will have a moment as well, clear. So the axial load produce normal stress, and this moment will produce bending stress. So your stress will be equal to N by A, which is normal load, plus minus the stress produced due to bending moment. So My divided by I. Now you can see that due to this moment M, it will bend like this. So the lower portion will be in tension while upper portion will be in compression. So let this upper point is represented as A and lower point is represented as B, because we are going to plot the stress distribution along AA. So what we will do is that stress at point A will be compressive one, so it will be equal to N by A minus M into Y divided by I, while stress at point B will be tension one, tensile stress, so it will be N by A plus My divided by I. So we'll first find sigma A. Sigma A is equal to N is 80 kilonewton, so A 80 into 10 raised to power 3 divided by area. So thickness of this plate is given as 10 millimeter. So this is the height. This thickness is 10 millimeter, which is 0.010 meter, and height is 0.20 meter. So area will be equal to 0.010 multiplied by height, which is 0.20. Clear? Minus moment, which is 4 kilonewton. So 4 into 10 raised to power 3 multiplied by y. Y is distance from neutral axis till topmost, that is 0.1 meter. Okay, so we'll put 0.1 divide by I. I is 1 over 12 BH cube. So B is 0.010. Clear? And H is 0.20 whole cube. So when you solve this, you will get bending stress at point A comes out to be minus 20 into 10 raised to power 6 Pascal, or you can say that sigma A is 20 megapascal, and that is in compression. Okay. For this portion, we know that stress at point B is equal to N divided by A. N is 80 into 10 raised to power 3 divided by same area, which is 0.010 into 0.2, plus moment, which is 4 kilonewton, so 4 into 10 raised to power 3. And now you can see B, Y is distance from neutral axis till point B, which is again 0.1 meter. 0.1 divided by same I, which is 1 over 12, B, which is 0.010, and 2 H, which is 0.2 cube. So when you solve this, you will get sigma B comes out to be 100 megapascal. 100 into 10 raised to power 6 Pascal. So which means that sigma B is 100 megapascal. Since this is positive value, so we can see that sigma B is in tension. Now you have both these two values. So let me show you how to draw the stress distribution. So this is the plate. This is the half of the plate. Clear? The total height is 200 millimeter, which is 0.2 meter. Clear? This was point A and this was point B. So at point B, we have compressive stress, which is 20 megapascal. So 20 megapascal, if this is the magnitude of 20 megapascal, 20 megapascal. And at B, which is 100, we have 100 megapascal. So this is 100 megapascal. 100 megapascal. The upper one is in compression and lower one is in tension. So in between these two, there will be a point where this stress will be goes to 0, and then it will increase and will create extension or tension. So this is the stress distribution. Okay. Now you can see that this is the line where the stress is 0. So this is actually its neutral axis. In order to find the distance of neutral axis, uh, what we will do is that is if this is total height 0.2 and let this distance is h, this distance is h, so this remaining distance will be equal to 0.2 minus h. Now you can see we have two similar triangle, one is this one and other one is this one. So what we will take the ratio of, if we take 0.2 minus h divided by the amplitude of stress or maximum stress 20, that will be equal to h divided by 100. Why? Because you can see that these are similar triangles, so the ratio of their sides will be equal. So from here 0.2 minus h divided by h will be equal to 20 over 100. So it means that 100 multiplied by 0.2 minus h will be equal to 20h. So 20 minus 100 h will be equal to 20. So 100 h will be equal to okay, this is 20h. So 100h plus 20h is equal to 20. It means that 120h will be equal to 20 and h will be equal to 20 divided by 120. So 2 and h will be equal to 1 over 6 meter. So h will be equal to 0.16667 meter. So in term of millimeter, h will be equal to 166.667 millimeter. So it means that below line or below plate, this portion of the plate, so h will be equal to 166.667 millimeter. When you go from this line to this point, so it will be its neutral axis. Neutral axis for this beam is that where the bending stress will be equal to 0. So this was this stress distribution of normal stresses acting along section AA, and that was all about problem 8-32. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. Also, all the links for the playlist is mentioned in every description box of the video, so you can go easily to description box and you can click on the link, so it will take you to the required playlist. If you have any question, you can ask me in comment section. Thank you for watching.